I don't know whether I need to use my or Al-Sultanullah. So thank you to Professor Ko for and your team for hosting the today's lecture. I was required to share a bit topic about visualization in the fluid flow method. The method of visualization in the fluid flow and thermal analysis. So this is actually the technique that I used in along my research field until now. Okay, so in a layman term, the method is benefiting the glowing of a liquid. Okay, so from the glowing area you can measure the properties that you wanted to measure. Okay, so how and what makes the liquid to glow, it depends on the Florence dye dissolved in the liquid. Okay, so as you can see, this is a liquid. This is a general picture anyway. Liquid glowing by the irradiation of a laser source. Okay, so from the glowing part, let's say you turn off the light and make the room dark, you can only see the glowing part. So you can measure the intensity of the glowing light to read what you want to read, especially temperature or maybe pH or the layer thickness of the liquid itself. Okay, so it's a non-intrusive method, meaning that the probe will not disrupt or disturb the natural flow of the fluid area. Okay, and in fact when you dissolve the Florence dye into it, it will not change the chemical properties. It will just change the optical properties which you will need it for the measurement of the investigation in your area. Okay, so actually it's already started half a century ago, okay, by a Japanese researcher and Mark J. Dreyer and the David professor. So what they have been investigated is to measure these hydraulic radical molecules inside a water flow. So as you can see, I don't know whether I can use this. It's not detected, right? Okay, as you can see, this is the part of the result obtained by Mark and David. Okay, so they want to track the flow and how much it is, meaning that the concentration of the hydraulics radical inside a burning flame. Okay, so as it goes up, okay, the concentration decrease, and this is like the flow, trending of the flow of that chemical, the molecules. Okay, so this is based on the dye that they use is coumarin 153. Okay, to check to make the burning flames glow with the Florence dye inside it. Okay, so the working principle is actually a very simple one, especially if you are working with the visualization method. You will use most of lasers, right? So it's applying the shift stop phenomena, which means when you irradiate a liquid with this Florence dye, okay, it will give the energy of the molecules to excited, right? when you irradiate a laser, but it will be only temporarily. Then it will goes down to the ground state. But when it goes down to the ground state, the wavelength of it goes down to the ground state, the molecules will let the liquid to be glow or fluoresce, but in longer wavelength spectrum of a spectrum. So as you can see, after it goes down to the ground state, then it will appear in the longer wavelength for the emission. So this fluorescence intensity will provide you information. What kind of information that you want depends on the dye that you use. Okay, and the dye that you use must be, the absorption spectrum of the dye that you use must be matched with the laser spectrum. So specific dye will be needed for a specific laser. So you need to be careful with the wavelength of the laser itself. Okay, sometimes you use the when you use, let's say for example, you use a rhodamine B dye, it is specific for only monitoring the temperature, but this kind of dye can be only dissolved in water. You cannot use other than water to make the dye dissolve in it. And you need a special one laser, which means the rhodamine B is absorbing the energy at peak around 550, something like that, 550 nanometer. So you need that kind of laser that can make the molecules to absorb this energy at a specific wavelength. Okay. So as I said just now, okay, you need the dye. You need the dye to be dissolved in the liquid, and then you need a specific laser. Okay. One of the advantages in using this kind of method is you can measure whether 1 point or 2-dimensional area or 3-dimensional area. So you can put multiple dyes and multiple lasers to measure the location of what you want to measure. Okay. For example, this one, it is a PLIF, means planar laser induced fluorescence. So we irradiate a laser sheet pattern. This is a laser sheet pattern. So they need the sheet optics to project the laser beam from dotted pattern to sheet pattern. Okay, so what happens inside the laser sheet depends on the fluorescence intensity of that liquid part. So you can read the properties that you want based on the image you take, or maybe you can read by using the spectrometer to get the intensity, the wavelength of the fluorescence intensity. So for example, for this one, they use the CCD camera to make use of the image taken, and then they process the image, read the intensity of the fluorescence light, and calibrate to read the data that they want. Okay, so usually people use this kind of method to read pH of molecules inside the liquid, or maybe you want to know the concentration of the molecules, or you want to read the temperature. Okay, or maybe you want to get the layer of thickness inside that liquid. Okay. Okay, so 3D measurements are possible by scanning multiple planes. Okay. For example, this one. Okay, this is another method used by another researcher. So this one, he investigated what we call the mixture of hot and cold water flow. Okay, to find it used the rhodanine B to read the temperature gradients, okay, and then at the same time he combined with using the particle image velocimetry to track the velocity of the hot water flow and the cold water flow. Okay, so it is a versatile method that you can combine with another visualization method actually. Okay. So another one is a Japanese researcher. Okay, he wants to read how heat moves. Okay, and how is the pattern of the clumps and the ridges above the hot surface. Okay, so this one is also using the rhodanine B. Rhodanine B is a very useful dye to measure the temperature analysis. For example, another one is fluorescein, also can be used to read the temperature. Okay, but of course, before you can project the real experiment, you need to have calibration so that you can relate between the temperature and the intensity of the fluorescence light before you conduct a real experiment. That is the most important one. Okay, next one I will show you. This is the graph showing you the dyes, multiple dyes that usually used in measuring the temperature. Okay. As you can see, there are fluorescein, even fluorescein 27, rhodanine 560, rhodanine 6G, rhodanine B, KR, and another rhodanine and SRH. So these are all the dyes that can be used to measure temperature. But each of the dye has its own absorption spectrum. So for example, as you can see, the green one, that is rhodanine B. Okay, it can absorb energy, the peak at 550 nanometers. So you need to have a laser that is having the same range, okay, as closer as you can be, so that it can absorb maximally the energy and excite to a longer wavelength, so it can fluoresce maximally. So that green one, rhodanine B, it will fluoresce at nearly 600 nanometer wavelength. Okay. So the fluorescence intensity will be longer than the absorbed spectrum. Okay, so you can choose which one that you want to measure. Okay, other than that, you must be careful with the power of the laser. The better, the larger is the power of the laser, the better results that you can have. But it doesn't mean that if you have lower power, you cannot have accurate results. It's totally fine, but you can adjust with the concentration of the dye you dissolve inside the liquid. It can compensate the power of the laser that you use. Okay, what is another one is, okay, so another one is different dye also react differently according to the temperature. Okay, as you can see, the fluorescence signal read by each dye different from each other. Okay, the rhodanine B, the green one just now, okay, it can read around 56 degrees Celsius maximally. Okay, and also each of it will have different trending, which means some dyes will give you increasing trend with the increasing temperature. Okay, so increasing trend with the increasing temperature. For example, for the fluorescein, okay, and fluorescein 27, it will give you trending with increasing uh, signal or intensity of the fluorescent light with increasing temperature. But some dyes will give different results, which means if the fluorescence intensity is larger, okay, sorry, if the temperature is larger, you will get the signal of the fluorescence as decreasing, it more darkened. Okay, so different dyes give you different trends. Okay, don't be surprised when you get the result as decreasing. Okay, it's totally fine with let's say for rhodamine B and also for the QR. Okay, so uh, another one is you can check the what we call the accuracy, or the larger the trend, okay, the larger it goes up or the larger it goes down is better. So usually people will use fluorescein or they will use rhodamine B because these two are giving you the better results. Okay, because the trending is more obvious and visible. Okay, so this is the what we call as fluorescence calibration. Firstly, when you before you run your experiment, you need to make this kind of calibration to get the relationship between the fluorescence intensity and the temperature, specifically for temperature. But maybe for a layer of thickness, you need to do another calibration. You need to find the relationship between the layer of thickness and the fluorescence intensity of the liquid. So I will show you the example of my own experiment. Okay, because I am affiliated with a faculty of manufacturing, so I run a simple experiment to investigate the lubricant flow during a machining process, a milling cutting process, okay, which lubricated by a minimum quantity lubrication method, okay, meaning that the lubrication delivered to the cutting area is in a mist or fine droplets pattern. So I want to know or to clarify the layer thickness of the lubricant between the cutting zone, between the cutting tool and the workpiece, the surface of the workpiece. Okay, so what we need is these are all the setup of the machine. Okay, so I will use a simple diode laser to activate coumarin 153 fluorescence dye. I use coumarin 153 fluorescence dye dissolved in the lubricant oil. Okay, so this dye is having maximum absorption spectrum that match with the diode laser spectrum. Okay, in a green laser. Okay, so as the machine run to cut the workpiece, okay, we turn on the dye and investigate what happened with the layer of the thickness of the lubricant. So we need the optical flat because we use it for calibration method. Later on I will show you in the next slide. Okay, and we also need a green filter. This green filter is used to gather maximum intensity of the fluorescence light appeared by the lubricant. And then we record the image by video camera, and we process it into image and get the intensity of the fluorescence light. So by looking up into the lubricant flow, we can relate what happened with the finishing quality of the workpiece. Is it the better quality of the workpiece is having larger or thinner thickness of the lubricant? Then we can relate the thickness with the surface quality. Okay, so this one is, as I said just now, before we run the experiment, we need to calibrate the relationship between the light intensity and the oil film thickness. So what we did is we use the optical flat. By using the optical flat, we sandwich a known thickness plate into the raw workpiece that we want to cut. So it will make a gradient thickness layer, right? So the laser that I use is not a dot pattern. I use a line pattern laser. So we just irradiate up from up above. So darken the room, then you will get the fluorescence intensity of the liquid in a thin sheet layer. So we will read the thickness from the very initial point to up to the largest thickness area layer. Okay, so for this Kumari 153, it will give you trending as larger thickness is having the larger intensity. Okay, so you will get this what we call the linear equation. So by the linear equation, once you run the experiment, you read the intensity, then you will get the thickness of the layer of the oil. Okay, we use a curtain-like sheet to avoid the light, another light to come into the machining area. Okay, once we turn off the light. Okay. So this is the final slide I will show you. Okay, so what happens to the lubricant oil? Okay, we run the experiment with slightly different flow rates of oil lubricant. Okay, so the larger the lubricant, it will give you the larger of thickness layer inside the machining area, inside the cutting zone between the cutting tool and the workpiece. Okay, so as you can see, maybe below the 150 milliliter per hour lubricant, it will not give you obvious change of thickness. But as you make it larger than that, you will find that at the mid stages of the cutting process, the layer of the thickness will slightly goes down and go up above. Okay, because this is called as temporary thinning of the lubricant film. Okay, during the mid stage, the contact pressure and the temperature reach at their very peak one. Okay, so the temperature increase and it will make the lubricant to be harder and difficult to penetrate inside the cutting zone. After that, it will just stop it and finally make the lubricant to be easily to penetrate the cutting zone. Okay, and finally until it is stopped. This is the distance from the machining starting point. We have 120 millimeter area of the cutting zone. Okay, and from this pattern of the layer thickness of the lubricant, we relate with the surface finishing quality. As you can see, it's slightly, this is the surface roughness. it reads better roughness along with the larger lubricant oil. Okay. Another one is what we have done is, I didn't show you here, but we have another parameter that we use are using the largest cutting speed. Okay, as we increase the cutting speed, another layer of thickness of the lubricant will become larger. Okay, this is because of the hydrodynamic changing inside the cutting zone, cutting tool, and the cutting surface. Okay, as you running the machine as faster than that, then you can get the lubricant to be easily penetrate the cutting zone, and you will have the same trend like this. Okay. Now I didn't prepare the slide, but now I'm currently working on the temperature analysis using rhodanine B to get the temperature of the lubricant during the machining process, the same process, but I want to read the temperature. But we are still in investigating process because the temperature of the cutting process is much more larger than 100 and 1000 degrees Celsius. So rhodanine B cannot work like that. We need to change the dye, or maybe we need to adjust the concentration and combine other dyes, maybe multiple dyes, to read that kind of measurement. Okay. So that's all, maybe.
Okay. Thank you. Professor Rosli provides them how to monitoring the fluid flow and temperatures, and then she gave also some example of the application. So please, if you have any even basic comment or questions, please ask any questions. Please.
Yes, sure.
Thank you for the nice presentation. So you use laser to measure the temperature within the fluid, and
Yes.
the laser itself has really high density, high dense energy, which means that it might increase the fluid temperature and also affect to the particle itself. So,
Okay.
simply speaking, it might increase the temperature of the fluid and also the particle itself. So how can we calibrate, or how can you consider the temperature increase from the laser?
For that's why you need a specific dye that can compensate the increasing temperature caused by the laser. So the dye will have. Do you know the quenching process?
No, not really.
Yeah. So the quenching process inside the liquid, and also the dye, let's say for example rhodanine D or rhodanine 650, it will compensate with the temperature caused, the high temperature caused by the laser itself. Okay, so you need to adjust the concentration to make the temperature read by the fluid intensity, fluorescence intensity. It's influenced by the temperature caused by the laser, right? So you need to firstly calibrate it by using without the dye itself. Firstly, you need to calibrate without the dye itself. Then you need to make another one to calibrate it with the dye. Then you can simply put into the equation of the laser. Then you can neglect, or you can reduce the influence of the temperature caused by the laser itself.
Is there any other method to suppress the
Yes.
temperature increasing
Yes.
from the laser?
Yes.
How can we do?
You need to make multiple calibration. That's why I haven't get the similar result to a better result to get the reading of the temperature because of the temperature of the laser itself.
I have one more question. Apart from this fluorescent intensity technique of measuring the temperature and other parameters, what are the other options available?
Okay.
Or why we need to focus on utilizing this technique in comparison with the other available options?
Because for this technique you can measure multiple plane. You can use various laser and combine with various dye, so measure what you want to measure, and so you can combine with the another visualization method to measure the other properties. And this is not intrusive. Other may be also a non-intrusive method, but this one, it will not change the liquid properties itself. It will not change the you can just get the optical change of the liquid fluorescence from the dye activation. So and then usually when you use a non-intrusive method, the cost will be higher, right? But for this one, we just use a very low cost diode laser to get the fluorescence intensity.
So basically, simplicity and the cost effectiveness of
Yes.
this technique is get precedence over that.
Yes.
Thank you.
When you consider the cost, maybe you can choose this method.
Okay. Any other questions?
Yeah, sure.
Thank you for your advice.
Okay.
What is the geometrical resolution of the temperature using this LIF?
Okay. The geometrical
Resolution.
resolution.
Yes.
You need to have a very good camera. So 1 micrometer pixel area depends on the temperature that you read. Depends on the intensity of the image. Other than that, you can use spectrometer to read the not intensity of the light, but you need you read the spectrum. So to avoid the what we call the lower resolution appeared by your intensity of the image, you can use spectrometer to measure the wavelength appeared by the liquid that is fluorescence from the dye activation.
Okay, any other questions? I have very small question. So if you utilize the camera, then also recently a lot of improvement in the camera image processing.
Yes.
So do you, for example, there are the low resolution can be converted
Yes.
into high resolution
Yes.
using the AI or some
Yes.
additional algorithm. Is there any trial to improve the quality of the resolution using any others like the image processing algorithm or AI based algorithm?
Yes, we can adjust the programming of the camera that reads the intensity. So because my faculty is manufacturing and mechatronics, so I have a mechatronics student to develop a programming method to increase the resolution of the image taken by the camera. So they adjust the programming, still ongoing. The research is still ongoing. So they adjust the programming method, Python programming method, and to read the resolution to what we call to avoid that lower concentration. We can still use the low cost camera, but you need to adjust the reading of that intensity of the fluorescence light using the programming or AI.
Okay.
But of course you need to make it multiple data, very big one data, so that your result is reliable.
So when I basically my research topic is more like the robotics and
Okay.
so maybe I'm not expert on your field,
It's
so
okay.
do you think it's possible to use the dye-based measurement for the untransparent material, liquid?
Yes.
Is it possible? So
Possible.
for example, the very sticky and opaque
Yes.
material can be used with the dye
Yes.
as well.
Yes.
Is there any example of that one as well?
For the transparent one, we have used rhodonine with water.
Non-transparent material.
Non-transparent material. I think I haven't used it, but we need to check first. I still don't know whether it's possible or not.
Because using the camera, non-transparent
Yes.
information cannot be obtained, I
Yes,
guess.
yes, exactly.
Okay, so any other question for Rosli?
Thank you also for your talk. And I want to like ask about for example, you are using the lubricant, which is like a viscose like fluid. So I just want to ask, is there any like differences? For example, if you are using lasers, and then we excited to the like viscose oil.
Okay.
And is there any like, for example, like because of the scattering,
Yes.
the behavior of the liquid through the index
Yes.
of the oil? Is there any like difference between the water?
You can neglect that part, but you have to use a better angle.
So is there any like
Angle.
additional like calibration or like the post processing that we are requiring?
If you have a very thick layer of thickness, you have to slightly use angle more than from the surface around 30 degree to 45 degrees degree angle. But if you have thinner than that, thinner than maybe around micrometer thin, so you can use the angle with maybe 90 degree from the surface, but you can neglect that scattering part of the laser. Of course, you have to have that Raman scattering equation that you have to use inside your experimental results.
Okay. Any other questions? Okay. Then please give a thanks
you.
to her.